Good afternoon all. Thank you for joining this webinar. The title of today's conversation is Selecting the Correct Pump for Your Application with a focus on the anaerobic digestion industry, as you can imagine. Thanks for taking the time out to listen to this. This is meant to be a thought-provoking conversation, which isn't meant to take any position of any sort of brand representative from Atlantic Pump's perspective or any other manufacturer, but really just to share some best practice within the industry. Unfortunately, today we had Flavio joining from the AD and Biogas Association, which unfortunately he can't attend this afternoon, which is a real shame. But I've got some other industry experts that I'm going to call on through the call, including Martin Gilman, who's been in the pump industry, progressive cavity pump industry for over 25 years. So look forward to hearing from you, Martin, and others as we go through. So first of all, we're going to touch on a little bit of an introduction to who we are as hosts for this webinar. At Atlantic Pumps, we've been in the mining industry for many years. Our focus is in the heavy industrial sector, and that's taken us naturally, as you can imagine, into the anaerobic digestion sector. The AD sector is a relatively new sector and comes with some new challenges, but with a background of heavy and abrasive applications in the mining industry, something that we understand relatively well. I've been with the company since we started in the UK. Our history is based in South America and Australasia, but been in the UK now for over 10 years. We're sharing some of my experiences in the anaerobic digestion sector and looking forward to any questions that will come up at the end of the call. So let's kick off with a few industry insights. Well, first of all, we know that this is not an industry that's going away. As everyone that's on the call knows, this is an industry that's only going to grow and develop, especially with the drive and change in legislation around segregated waste in the UK, meaning that it's more and more economically feasible for councils to send their food waste to anaerobic digestion, and it makes more and more sense. The other sectors that are obviously driving anaerobic digestion is of course the water industry, where they've found over the last few years that they can make a significant return and on the effluent they have at the end of their process, and use it to power their large and very costly plants, which obviously absorb a huge amount of energy. So what are the challenges that this industry faces? Well, we've just alluded to one there, and that's that with a huge amount of the processes in this industry are based on the technology that's come in some form from the water industry. And the water industry has got years and years of process experience, but the sort of materials that the AD plants are coming across in the form of real nasty contaminants in food waste is something that the water industry has never really been presented with before. Therefore, a lot of the technology that's in play isn't absolutely suitable for the challenges in the AD sector. Just for example, what's called sludge and abrasive material in the water sector will be a consistent material with a bit of rag. What's called abrasive and aggressive in this sector could have significant pH variations, could have large solids, could have knives and forks in it, depending on the waste stream. It's also one of the other significant challenges in this sector, especially when it comes to moving around solids and pumping applications, is that there is a bit of a perception for some reason that certain levels of wear are acceptable, and of course that is the case. But the technology that was in play when the AD market kicked off in the UK, going back 20 years, and the technology that's available today are two different things. So wear life, there should have been a progression on that journey. This would probably be an appropriate moment to call you in, Martin. Have you got any comments around the challenges that face the anaerobic digestion industries, particularly with focus around pumping and solids handling?
Thank you, Nathan. Hello, everybody. Yeah, I do. Not much more to add, really. I think you've covered most of it. The industry challenges, from my perspective, as you touched on, over 25 years of serving mainly wastewater treatment, actually, but significant amount of time as well in the AD biogas industry. It's around reliability, and that's certainly in what is certainly one of the more challenging industries. And it comes down to less failure being directly proportional to how much you spend on your expensive parts and your downtime. So really, whenever I'm approaching the industry in any kind of consultative way, I'm looking at maximizing uptime for end users and others, really. So the three things that jumped immediately to my mind from experience are often the end user does get little or no choice in what they start the plant with, because the plant builder may have selected that, or other consultant may have selected that during the design stage. So you get what you get, and you got to start working with it. And it might not always be exactly what you need, because things change within the waste stream, again, as Nathan's already touched on. So yeah, I think those are the main sort of things. So it's getting what you've got and trying to get the best out of it, and if necessary, making changes and moving forward to more modern or different innovation, if you like, so that you can get that reliability right up there and reduce the overall cost of ownership. So yeah, I pretty much concur with most of the things you said there, Nathan.
Cool, thanks, Martin. We'll come back to some of those points you made there shortly, particularly around what you said about ease of changeover. That's a real challenge. I think another challenge this industry is faced with is quite an isolated industry. Being quite a niche and a small industry, there isn't a huge amount. There's plenty of networking going on within the industry, but not a huge amount of networking going on outside the industry. Does that make sense to you, Martin?
Yeah, absolutely. Yeah, I would agree.
So one of the ideas that we would encourage is obviously there are industries out there that have got significant wear challenges. The mining industry would be one of them. Heavy industries. There's plenty of other applications out there to encourage AD plant operators to network with people that are outside the industry that have got maybe been suffering with the challenges that the AD market is faced with for much longer. I think as we go through this presentation, there's a few other bits to pick up on as well. And one other thing I just wanted to highlight before we moved on from this segment was the introduction of the Industrial Environmental Directive, which came about 2.5 years ago, following a significant industry event in the water industry, which is driving change around the management of digesters, both in the water industry and more widely. That in itself will present significant challenges around accessibility to digesters and the frequency of cleaning them, which is a real challenge to this segment. I'm just going to move on and have a look at just a few common applications within the AD market from a pumping perspective. Now, this is by no means extensive and doesn't cover every application, but it does just pick out a few common problematic applications that are worth looking through. I've highlighted 4 on this. First of all, thermal hydrolysis, looking at digester recirculation, sumps and site drainage, and the pumps that are situated in any sort of depackaging applications typically in the reception hall of a plant that's maybe receiving waste stream, such as a black or green bin waste. So starting off with thermal hydrolysis, one of the key challenges here is obviously temperature. This is a really problematic application. One advantage is that it's typically in a part of the process where you've got consistent solids. A lot of sites have gone down the road of introducing ram pump technology into this application. Ram pumps are fantastic pumps, but one of the core challenges with ram pumps is the ease of maintenance. You require skilled labour to keep the units operating, and when they're running, they run well. When they fail, they tend to fail with exorbitant costs associated with them. So it's important. What we're working towards in this webinar is getting an understanding of total cost of ownership. It's important that when looking at the thermal hydrolysis applications, you consider that this is a very challenging application, but the thing that to be considered most of all is the temperature. Martin, you've probably got some experience in this application from a progressive cavity pump perspective.
I have, yeah. I've a lot of experience actually with thermohydrolysis. At one point in my career, I was lead engineer for a pump manufacturer to get the right design specification, the correct build for Canby, who many of you might know are one of the main worldwide leaders in the design and implementation and build of thermohydrolysis plants. And yeah, right back from the very first plant in Ringsend, just outside Dublin, a lot of work went in there in research and development to get, in that case, a progressive cavity pump to function with at least some reasonable amount of uptime. And in the early days, it was very, very difficult. All sorts of technologies were tried, and all sorts of manufacturers had a go at it. But one or two stuck with it. And today, you'll only mainly find two brands that are relatively successful with thermohydrolysis. Very difficult to do. You have to consider huge amounts about the thermal expansion, not only of the rotor within the pump, but also the elastomer and the stator itself. Without, excuse my phone going off, without teaching people to suck eggs, one of the most important things about most positive displacement pumps is the interference fit between the two main elements of the pump. And with a progressive cavity, we call it the clamp, so the tightness, the fit between rotor and stator. And of course, you have to allow for the thermal expansion of the machine, so that is correct at the actual duty temperature. Not only that, but when waste sludges get very hot, they also get far more aggressive. There'll be no surprise there. The properties change quite dramatically, and you also get issues with absorption of certain. I'm no biologist, I'm no chemist either, but certain properties of the sludge into the elastomers themselves, and those can implode and explode and cause hysteresis failures, all sorts of things. So very, very challenging indeed. And in most cases, those kind of plants are aiming just to get from shut to shut, from summer to summer, without catastrophic failure. That's how a regular can be. But the tip of the iceberg with that topic is just the pure cost of it, because they are slightly exotic pumps in their material makeup, and so therefore every repair, every maintenance intervention, you can look at significant costs. I mean, I'm talking £15,000 to £20,000 per repair. So it's a big talking point across the UK right now. There are, I think, about 20 thermohydrolysis plants in the UK, maybe more since I was last in one. And so, yeah, it's a big topic point. And so, yeah, significant experience there. But I can tell you that lots of advances have been made over the years. And it's not really about abrasion with hydrolysis. Sorry, yeah, it's mainly about the thermal expansion issues and how it changes the structure of the pump once the pump gets hot.
That's really useful. Thanks for that, Martin. And we can, I'm sure anyone with any challenges can pick that up separately with Martin as well. I think that we're just going to move on to digester recirculation. This again is a real challenge, especially as the fleet of digesters in the UK AD market grows old and more grit is present in the digesters. Obviously, grit comes with challenges with wear life and other challenges as well, but most significantly with wear life. Typical pumping technology in this sort of application has often been chopper style centrifugal pumps. So a wide variety of manufacturers in that sort of application. In other sites would use progressive cavity pumps for this. It's important to consider a few things in this application. One is that obviously you've got the back pressure from the tank. You've got a tank full of abrasive and aggressive liquids, typically maybe between 4 and 6% dry solids, and you've got that pushing back on the pump every time that pump is in operation. To put it in layman's terms, it's what we call obviously a pressure that is causing strain on the seal, and when the seal is strained over time, you will end up with leakage, seal failure, eventually bearing failure, and significant costs associated with that. One of the things that we've seen in this application is when standard centrifugal pumps designed for the water industry are put in this application, they don't tend to have any form of sacrificial liners. They tend to be a one piece volute. When that volute wears through, you've got significant costs associated with replacing it. Whereas if you can look at some sort of technology that's got a sacrificial liner, or replacement impeller that's easy to maintain, that's definitely a benefit. I think that in our experience, we have introduced high chrome line centrifugal slurry pumps that have got a background in the mining industry. This application is actually remarkably similar to thickener underflow applications, which are prevalent in the mining industry. And it's important to understand that when these pumps are specified, as Martin alluded to earlier, not just in this application but more widely, often the two considerations are around capital cost and efficiency on the day they're put in, which isn't that relevant when 2 or 3 weeks into a plant being up and running, the efficiency could have dropped away significantly because the pump's not designed to handle the level of abrasion that's present. So what we like to discuss instead is whole life efficiency. It's important that you select a pump that's going to be efficient for the duration of its life, or as long as possible in its life, and it's particularly appropriate in this application. I think we'll move on to sumps and drainage applications. So this is a relatively minor application around sites, but I put this in here because it can be a kind of runaway cost on a lot of sites. Sites could be using small submersible pumps that are not designed to handle the pH levels that are present around site, and this is the sort of thing that a site could be spending a couple of £1,000s a month replacing submersible around the site to keep the site clean and tidy, keep it compliant from a health and safety environmental perspective, and very quickly it can add up. It's important, obviously, to maintain that level of the cleanliness around the site, but picking a pump that's actually designed to cope sitting in a well that could be running levels of pH, it could be handling grit, rag, anything that runs out through the process. It's important that that process, that particular application is considered with the level of severity that it actually deserves. And then finally, whilst we're looking at applications, I just wanted to touch on the DPAC area, and I'll be glad of your contribution shortly on this, Martin. But this is a really challenging application. So for everyone, I'm sure everyone's aware, but this is where the fresh waste stream comes into the plant. It is received, as you would know, in a variety of different standards. Sometimes good, consistent feed, but other times full of all sorts of foreign objects, everything from knives and forks through to hard plastic packaging, bones, eggshells, a wide variety of materials that will cause any pump that's out there a significant amount of damage. The pumps are great when things are consistent, but often challenged when there is an inconsistency, particularly in solids type or density or profile. So, and this is what this application throws at it. You may have a simple agricultural feed that in the morning, and in the afternoon you could have you could be adding honey, or you could be adding a wide mixture of feeds, and that's a challenge for any pump that's sat in this application. One of the significant challenges, obviously, is the size of those solids. It's many pumps that are out there, their efficiency is based on their tolerances, and so you've got to consider that for a pump to perform, it's got to be able to pass large solids in this application, and that runs in contradiction to how typically a progressive cavity pump works, or even any sort of positive displacement pump largely. I heard of a site the other day who was spending £500,000 a year on a pump application in this very application, because the pump that was there just simply couldn't handle the size of solids that were coming through, and this particular site had done a huge amount of work to stop those solids coming through. That's obviously the preferential choice: is how can you stop pieces of steel, pieces of wood, large plastic items coming through the process. But if you can't do that, and you're not always in control of that, then it's important this pump is a bulletproof pump in this application. One of the common pumps in here would be a Putzmeister style piston pump. Again, great and bulletproof, but extremely complicated to maintain and extremely costly when they fail. It's important that's taken into consideration. You really want a pump in this application that's easy to access, easy to maintain, and is designed to last as long as possible. We've had some really positive experience with peristaltic hose pumps in this application. Obviously, they've got to be large enough to handle the flow, that's required in this application. And obviously, in some instances, depending on the setup of your AD plant, there is some plants are run on batch control. So maybe you want to introduce 10 meters cubed of a particular material. Other plants are run based on a measurement of flow consistently into the process. So it's important that taking into consideration a peristaltic hose pump wouldn't be suitable if you were measuring a consistent flow rather than batch process because of the pulsation. It's also important that you consider the things like blockages as well. With large material present, you can get a build up in a pipeline. You need something that's got adequate ability to keep product moving, and solids velocity is particularly important to consider. Martin, glad of your contributions on this particularly challenging application.
Yeah, I mean, DPAC, yeah, is always a head scratcher, and I think most people that have pumps in that particular application will be more than aware, and they won't need anybody to point out what challenges there can be. The first thing you've kind of touched on really is all about pump protection. So before you even consider what the pump is, what type, how you're going to use it, is how can you protect it? So we're talking some basic things like stone traps, metal traps, magnets, anything you can do really to prevent what should not be going through it. Often that can't be necessarily or easily done, and we get that because crushed glass is a common one that I've come across, but I've pulled out all sorts of things: padlocks, knives, forks, spoons, the whole thing. So the first thing is, pump protection without question. But after that, really, you're just following in my field within progressive cavity pumps. Really, you're just following what I call the 6 key points for consideration anyway when specifying the pump. The important thing, if you can have any say in it whatsoever, is to get it right first time. I think we've already touched on that. To repeat it, but the first thing of the 6 points really, and I can feed this over at some point to Nathan, who can distribute it to the attendees if they wish to. The 6 key points in no particular order is number 1 is the pump speed. Okay, so you have to watch that pump speed, how fast you're running it to achieve the duty flow that you're looking to achieve for your stream. There's a part of the parlance, if you like, within the pump world is something called rubbing velocity, and the way that I help people understand that is if you get a normal razor or rubber, as we call it, and you rub out your pencil markings with it. As you rub it, you'll get that residue of rubber left on the paper, which you normally blow or wipe away. Okay, that's an exaggerated idea for your head about how that happens within a progressive cavity pump, but it's a similar kind of idea. Okay, so the harder and the faster you rub it, the more material you're going to pull off of it. So if you are pumping an abrasive material between a rotor and stator, you want to bring that rubbing velocity down to the absolute minimum, and all manufacturers can give you that figure. It's often not offered up front with a quotation or with a specification, but it is always going to be there. It should be in the software. So ask for that, and as a rule of thumb, you want to be on highly abrasive liquids. You really want to be less than 1.5 meters per second, okay, because anything more than that and you're putting significant wear, not only from the abrasives within the liquid itself, but also just between the elements of the pump. So that's the first one. So get that speed down. If you can operate under 100 RPM at the rotor, that's probably a good rule of thumb there as well. Nathan's touched on solid size. Is it soft? Is it soft? Sorry. Is it hard? Is it, if you were to measure the typical or the larger solids that you might expect, always work on a worst case scenario. Are they suitable? Will they go through the pump? Are the cavities within the pump in the PCP case sufficiently sized? Pressure rating, of course. What pressures you can develop. Again, work on worst case scenarios. Don't just look at the pipelines in front of you and a quick K factor and think, oh, it's only going to be this, because that soup is going to change. It's going to get partial blockages. It's going to get mass build up in certain areas, and that's going to give you a little bit more back pressure than you might expect. The pressure rate I've touched on. Temperature we kind of touched on earlier on. Thermal expansion, things like that. Things get hot not only from the material going through it, but also because of the friction between working components within a pump. Chemistry, Nathan's touched on that too. What are you putting through it? If you're a food reception plant, it could be fruit juices, it could be meats, it could be yogurt, whatever it is going to be, is going to change the challenges to the pump in different ways, okay, especially on the chemistry side. Certain elastomeric materials do not like natural fats, for example. So if you're going to get natural fats, but that's not the main thing, it just could come through now and again, you still have to consider what might be coming through that pump, even if it is sporadic and just depending on what comes through the gates. And finally, viscosity. What is it going to be like when it's come through the hammer mill, or whether it's come through the depackaging machine, whatever kind of thing you're using? What is that soup viscosity going to be like? If it's very, very thick, if it's what we might call non-flowable, then you might need an auger feed screw or an element like that to help work the material into the pump itself. So pump speed, solid size, pressure, temperature, chemistry, and viscosity are the 6 key points. And if those have all been covered correctly, and with sometimes considering the worst case scenario, you're probably going to get pretty close to a reliable pump.
That's awesome, Martin, and that probably is an awesome segue into the important considerations for bringing down total cost of ownership in key pumping applications. That you've given some real practical points to go away and check there. Obviously, not every application sites have not in the fortunate position to select from scratch. They've often been given a problem on a plate, so they've got to work with what they've got. So I think it's important that everyone understands that on average across pumping applications in industry, some applications vary on this, but on average, if you consider 100% to be the total cost of a pump in its service, typically on average only 10% of that 100% is the initial capital cost. 20% on average is the cost to maintain and refurbish, and 70% is the cost to run the pump, so power absorbed, for example. That gives you an understanding, a bit of an insight as to why it's so important that pump selection is correct, and it also shows how actually insignificant in the grand scheme of things the initial capital cost is. So when these plants are typically put together in history, they've been put together by largely German manufacturers who have really done a great job of pulling together the process in general. But from a pumping perspective, often the individual equipment focuses around that capital cost and, as referred to previously, the efficiency of that pump running on day one, without a real focus on understanding, okay, if 70% of this pump's cost total life is efficiency, what's that efficiency going to look like in 2-3 weeks time once the pump's been running, and is this pump really going to cope with the level of wear that it's going to see? And I think that there are a few other factors to consider. Obviously, in really abrasive applications like we've been discussing today, that 20% to maintain the pump may be higher as well, but it doesn't mean you should accept that. I think that a few other things to consider around total cost of ownership is one, what we call Atlantic pumps, the hassle factor. How easy is a pump actually to maintain? How easy is it even to access? Are you reliant on external labour? Are you reliant on skilled labour to maintain that pump, or can an on-site fitter who's got a basic understanding of engineering maintain the pump? That's two quite different experiences. If you can maintain a pump on site, obviously you remove the need often for a spare, and you don't have to send the equipment away to be refurbished, which comes with costly repercussions. It is possible to do ROI calculations on the whole life of a pump. Obviously, when you've got a new plant, you don't know things like wear life, but on an application where you've had something installed for a long while, it is possible to do detailed ROI calculations, and that's something that we'd be very happy to work through. I think that, Martin, you've given some real insights on this already, but have you got any other thoughts on some considerations around total cost of ownership as opposed to initial capital cost?
Yeah, just one point really, and again, it seems often these things are the simple, obvious points, but now and again we look at pump selections and we sometimes think about cost of ownership, whole life costs, and it's got a huge amount to do with the energy consumption of the machine, and of course it has, because that's the constant, isn't it? That's the thing that's going to be, trickling the coins down the drain every single day. However, one way that's often approached is a smaller pump, smaller motor. I'm going to use 7.5 kilowatt, not 15 kilowatt or 18 kilowatt, whatever. And yes, okay, there would be on paper a direct provable, if you like, saving due to the reduction in cost of energy. However, if we're looking at the overall, so the net cost of ownership, then that is probably a drop in the ocean. Again, depending on what the type of pump is. With centrifugal types, we're talking something different. But in my game, in the progressive caddy, for example, it is one of the smaller parts of the whole life cost model. The larger part is the mechanics of the pump. Is it suitable? How does it wear? And the how many repairs you're going to do it. So to bring it down to absolute simple terms, so you might save a couple £100 a year by stepping down one frame size on a motor, but now that pump has to run maybe twice the speed at the rotor to be able to produce the flow rate that you require. So you're going to double, going back to the points I made earlier on, you're going to double the net wear effect on the pump. So you might be buying £5,000 worth of spare parts instead. So one step down in frame size of motor for a little energy saving and a tick in a box somewhere might actually be a little bit of a red herring, and it might be a bit of a false economy, because the pump's now going to have to do twice as much in order to get what you want out of it, and that's going to put significant wear on the mechanics.
That's a really good point, and really that comes with experience, doesn't it? And as you rightly pointed out, there's lots of things that can be proven or disproven on paper, but the realities of the practical approach to whole life ownership, whole life cost, and total cost of ownership, is that if you can work with partners that have especially got experience in other fields, they will bring that practical approach, which gives a more real life bearing to the total cost of ownership conversation. That's really useful. Thank you very much, Martin. And this is the point where I just like to open up for any questions that may be out there. I've got a couple that were submitted earlier, but happy to take any live. The chat function is open. If you want to pop anything on there or Q&A, glad to put anything on there. Whilst anyone's thinking of any points around that, have you had any particular success, Martin, around monitoring pumps for intervention points in this marketplace? It's a big buzzword.
In a previous life, yeah, I was on a steering group in the design of condition monitoring for pumps in abrasive conditions, and that was really an R&D project. It did result in a product for the company I was working for at the time, but I actually left that company before the thing was finalized, so I couldn't say exactly how useful that product is today. However, yeah, it was really about looking at the pump, taking as much data from as many different points of the piece of equipment as possible, and using very smart programming and algorithms to actually kind of predict, or try to predict, when a pump might be ready for its next maintenance intervention. So, of course, the idea being not only to avoid the catastrophic downtime, or normally higher cost because other components get broken in the chain, if you like, but also to enable proper planned maintenance to be put into place, just in time type maintenance. It was relatively successful, but I think that it's overcomplicating things, perhaps even over engineering it. Companies will do that, they innovate in order to stay ahead of the game, which is a good thing in a way. It's great for brand and marketing. However, sometimes things are slightly over engineered and not exactly necessary, where with most PD pumps, a pair of gauges, and a little bit of monitoring on energy use is all you really need, because with those very basic devices, those basic instruments, you can still, in many cases, get a feeling for how healthy that piece of equipment is. It's just about training and understanding how to use them and what to do with them, and that's very low cost. Training might be given for free by a supplier, for example. A pair of gauges is what, £100 or something like that, and fitting them, and then it's a bit, I won't get myself started, but as a bit of an old-fashioned type, I feel quite sad when I walk around as many plants as I do and see so very few basic instruments like gauges on pumping systems, because for me they're bread and butter. But no, I have done, and they were relatively successful, Nathan, but I thought they were slightly overcomplicated, very expensive for an end user to put into place in many cases. Really, it's about training and knowledge and using some basic instruments. And that can save a huge amount of time and money. And the water companies who I deal with extensively, day to day, and I deliver quite a lot of training. Actually, they're always hungry for that, because they recognise that that a good bit of training for their technicians and craftsmen and some operators is actually going to save them a lot more money than necessarily buying new equipment all the time.
Completely agree. I think that monitoring has its place, especially when you've got a consistent clean water application, but in the challenges that are faced in this industry, a huge amount can be picked up by, as you say, a drop off in pressure or flow, some current frequency analysis. And generally the people understanding what they're dealing with. Of course.
Yeah, I mean, but when we're talking, sorry, I probably should have just added very quickly, when we're talking about remote in particular, remote condition monitoring, for example, is very, very valuable. It's a different topic altogether. When you can actually, get information to your desktop or even to your smartphone, which you can do these days, then on remote, whether it's unmanned sites, pumping stations, things like that, then yeah, absolutely. Or even weekend working when we're down to minimum staff, you can that's where it comes into it. So.
Monitoring reports requires some level of consistency, and that's not something that largely these AD plants and applications are blessed with. Okay, well, thank you very much all. I hope this has been a useful webinar. If of course there are any further questions and you'd like to discuss any particular challenges that you may have, or give your own contributions towards what you've found your experience to be around whole life costs and retrofit applications, resolving problems from poor capital choices, we'd be very glad to hear those. If you reach out to us on the contact details on the screen, we'd be glad to talk. And if this webinar is felt to be useful and there's further more specific or niche discussions you want to raise, then we'd be very glad to pull that together. For us as Atlantic Pumps, it's important that we are understanding the challenges that are faced by the industry today. And these sort of conversations are a great forum to understand that and share what we've learned across a broad spectrum of both suppliers and customers and general industry partners. So thank you very much. I hope you have a great remainder of your Tuesday afternoon. Thank you very much, Martin, for your contributions. And we'll speak to you all again shortly. Thank you. Bye-bye.